This lecture will be about support vector regression. We have a set of points which are shown by these green circles, and this is the x-axis, this is the y-axis. So every point, the x-coordinate is the argument, and the y-coordinate is a function of the argument, which in this case is a straight line actually. We want to fit all these data point, the samples, onto a straight line, which is given by y equals w transpose x plus b. Now, just for convenience, I will color the points above the straight line blue and the points below the straight line red. We are not doing classification, we are doing regression, but I choose to color the two sets of points separately, just for clarity. Now, as with support vector classification, we have a bound around this hyperplane that we want to fit, and this is the tolerance, and within the tolerance, plus epsilon and plus epsilon, so that's 2 epsilon. Within this tolerance, as long as the points lie within this zone, the tolerance zone, all these points, including these points which are exactly on the margin, we incur no penalty. But for points like this, which lie above the allowable zone, we have a penalty zeta I plus. Likewise, for points that below this allowable zone, this green band here, we incur another penalty zeta I minus. So zeta I plus and zeta I minus are two sets of primal variables in our case. So let's set up our constraints. For these kind of points, this is the error zeta I plus, these points which lie on top of our tolerance zone. We'll call this tolerance zone, and Zi plus is greater than or equal to 0. And for points that lie below the tolerance zone, we have another set of errors, zeta I minus greater than or equal to 0. So these are the errors, and we want to minimize all the errors. We don't have to take the absolute values because we know that zeta I plus and zeta I minus are both greater than or equal to 0. They cannot be negative. For points that are here inside the tolerance zone, zeta I plus and zeta I minus both are equal to 0, and because this yi minus w transpose xi plus b is less than epsilon, and w transpose xi plus b minus yi is also less than epsilon. So the zeta I plus and the zeta I minus both are set to 0 for those which are in the tolerance zone or right on the margin. Anyway, so this is noting that this is xi, the x-coordinate of this point here, this blue point. This is epsilon, this green arrow, and this blue arrow is the error zeta I plus that denotes how far above the tolerance zone is the point located. And this is the y-axis, yi, the coordinate of the y-coordinate of our point. Therefore, this is yi, and remembering that this is xi, and this is the straight line y equals w transpose x plus b. If we plug in the value of xi, we get this height, which is w transpose x plus b. And that's why we have this relationship. This is yi, which is more than w transpose xi plus b. So yi minus w transpose xi plus b is less than or equal to epsilon plus zeta I plus. And likewise, for the red point, which is below the tolerance zone, for which this expression holds. So our primal problem is to minimize with respect to W and B this objective function half W transpose W plus C times summation I zeta I plus zeta I minus. And C is some constant. Note that zeta I plus and zeta I minus both cannot simultaneously be greater than 0 because either the point lies above the tolerance zone or it lies below. It cannot simultaneously lie both above and below. And these are our constraints. These are for the blue points which lie above the tolerance zone, and these are for those that lie below the tolerance zone. So we have these set of constraints, and zeta I plus and zeta I minus are both errors which are greater than equal to 0. And so we can set up the Lagrangian. So this is the Lagrangian L, and we have these are our primal variables, and these lambdas and mu's are our dual variables. So this is the objective function which I copy here, and then I take this constraint and multiply it with lambda I plus, and I take this constraint and I multiply it with lambda I minus. I take this constraint zeta I plus greater than equal to 0, and the corresponding Lagrangian is mu I plus, and I take this constraint and the Lagrangian is mu I minus, and so this is our Lagrangian. So this is our Lagrangian which I just rewrote, and now let's look at the stationary conditions. What we will do is we will take the derivatives of the Lagrangian with respect to the primal variables W, B, zeta I plus and zeta I minus. So differentiating with respect to W, the first term yields simply W, and this term here, lambda I plus times W transpose Xi gives lambda I plus Xi and the summation, and this term here, lambda I minus times W transpose Xi, again gives us lambda I minus Xi, and inside a summation over all points, and that is equal to 0. Whence we get an important expression for the weight W in terms of the Lagrangian and the points, sample points Xi's. W equals summation lambda I plus minus lambda I minus times Xi. Differentiating with respect to zeta I plus appears here and here and here. What do we get? Here we'll get a C. Here for this term zeta I plus we'll get a lambda I plus, and for this we'll get a negative mu I plus. Whence this is what we get. C minus lambda I plus minus mu I plus equals 0, which gives rise to two equations here. Noting that lambda I plus and mu I plus are both positive, lambda I plus has to lie within this limit within between 0 and C, and mu I plus is C minus lambda I plus. We'll have to remember this. Mu I plus is also between 0 and C, which can clearly be seen because both lambda I plus and mu I plus are positive, and C minus lambda I plus minus mu I plus is equal to 0. That's why both lambda I plus and mu I plus both lie between 0 and C. Likewise, if we differentiate with respect to the minus errors, zeta I minus, we get another set of equations. Lambda I minus is strictly between 0 and c, and mu I minus is c minus lambda I. Differentiating with respect to b, b is here, so we have only lambda I plus here, and we have b here again, and there's a lambda I minus, so what we get is minus summation lambda I plus summation lambda I minus equals 0, whence we obtain summation of lambda I plus minus lambda I minus equals 0. Now let's proceed to eliminate the primal variables from the Lagrangian. So I have repeated the Lagrangian here, which I rewrite here, and these are all the expressions that we derived earlier from the stationary conditions. Now these constraints, that lambda I plus and lambda I minus, lie strictly between 0 and c. We don't need it at this point during the simplification process when we eliminate the primal variables. So let's toss it aside, and what I'll do is I will see this is lambda I minus, and I'll open this parenthesis. This is lambda I plus, and I'll open this parenthesis, and I'll delete these constraints which are only needed later, not during this derivation. This gives rise to this set of equations. I have opened up the parenthesis here. Now I will replace the mu I plus and the mu I minuses with the expressions which I have derived earlier. Mu I plus is c minus lambda I plus, and mu I minus is c minus lambda I minus. That yields these expressions. Next, I see that I have c times zeta I plus and a minus c times zeta I plus. I have a c times zeta I minus and a minus c times zeta I minus, which I cancel out. Likewise, I have lambda I plus zeta I plus and a minus lambda I plus zeta I plus. I have a lambda I minus zeta I minus. I have a minus of lambda I minus zeta I minus, which I cancel out. That gives me this simplification. Then I will take the terms containing W, actually W transpose here. I'll move them outside this summation, and so that will appear as another set of summations in the first line, because I'm trying to group together the terms containing W together. That gives rise to this. I've moved those terms from the second two summations here. And now I note that lambda I plus minus lambda I minus is equal to 0. I have minus lambda I plus here and a plus lambda I minus here, and they are both multiplied by the same constant b. Therefore, they cancel out, leaving me with this. And now, since I have derived an expression for W in terms of lambda I plus, lambda I minus, and xi, I do this replacement, and that gives me this as my final Lagrangian, where I have eliminated all the primal variables, and as a matter of fact, I don't even need the mu's, because I have expressions mu plus lambda plus equals c, and mu minus plus lambda minus equals c. Therefore, mu's are redundant. So this Lagrangian is now only a function of the lambdas. And this is xi transpose xj, which would later on yield the kernel. So this is my Lagrangian. And with this, I can write my dual. So I maximize with respect to lambda plus and lambda minus this is what remains of the Lagrangian, which is now the dual function, negative half double summation of lambda I plus minus lambda I minus xi transpose xj times lambda j plus lambda j minus epsilon summation I lambda I plus lambda I minus plus summation lambda I plus lambda I plus minus lambda I minus times yi. And these are my constraints. This is what I had kept aside for later, and I also know that the lambdas are between this range. And since we impose this upper bound on lambda I plus and lambda I minus, that's why we are taking care of mu i's also being positive, because mu I equals c minus lambda I. Now, I can vectorize the objective function, and this is what I get. Minus half lambda plus minus lambda minus transpose times the kernel lambda plus lambda minus epsilon lambda plus lambda minus transpose 1 plus lambda lambda minus transpose y, subject to these constraints, which upon further simplification gives me this expression. What I have done is take the terms containing lambda plus here and the terms containing lambda minus here. And then I will let this vector lambda be given by lambda plus and lambda minus. So it's the dimension of this lambda is twice the number of samples. Lambda plus is a vector whose number of rows is equal to m, the number of samples. Same with lambda minus. So this is a 2n by 1 vector lambda. Hence, this is the dual. It's greatly simplified, and it's a quadratic. Minus half lambda transpose times this plus k minus k minus k plus k times lambda minus lambda transpose of this vector. That's a quadratic, and the constraints have been changed accordingly, and it's all based on this notation here. Lambda is lambda plus lambda minus. And this is the kernel. Xi transpose xj, but in general, it's the kernel of xi comma xj. Now let's proceed to see what the support vectors are and what the bias, how do we get the bias, which is b in our equation. That's the bias. Okay, so we have this schematic back again where I show several points. And so our constraints were for the blue points which lay above the tolerance zone. We had yi minus w transpose xi plus b was less than equal to epsilon plus zi plus. And for points that lay below the hyperplane, we had this as the constraints. And so the zi plus and the zi minuses were our errors, which were also primal variables. Now, corresponding to these constraints, we introduced duals, lambda I plus, lambda I minus, mu I plus, and mu I minus. Lambda I plus corresponds to this constraint, lambda I minus corresponds to this constraint, mu I plus corresponds to this constraint, and mu I minus likewise corresponds to this constraint. And then we have derived these expressions. So both the lambdas and the mu's, they're all the dual variables. They are all between 0 and c. And furthermore, lambda I plus plus mu I plus is equal to c, lambda I minus plus mu I minus equals C. And the complementary slackness conditions, which we haven't discussed until now, yield these set of equalities. So if I multiply lambda I plus with this constraint, I get this expression, and when I multiply lambda I minus with this constraint, I get this expression, and when I multiply mu I plus times lambda zeta I plus, I get this expression, and likewise for this expression, and they're all equal to 0, which means that either the constraint is 0, inactive, or if the constraint is active, then lambda I plus is, let me repeat that again. If the constraint is active, that is, it's an equality, then lambda I plus is greater than 0. Likewise, if this constraint is active, it's equal, then this lambda I plus is greater than 0. Otherwise, for inactive constraints, when they are strictly less than, then lambda I minus or lambda I plus, as the case may be, they are equal to 0. Now let's look at points that are strictly within the tolerance zone. I have shown these 2 points here which are strictly within this green band. So they are within the tolerance zone. And since they're within the tolerance zone, strictly within the tolerance zone rather, I have a strict negative, strict less than sign here and a strict less than sign here. And so our 2 constraints are both simultaneously inactive constraints. And there is no error, so zeta I plus and zeta minus are both equal to 0. Since both the constraints are inactive, lambda I plus and lambda I minus, the corresponding Lagrange multipliers, have to be 0 from the complementary slackness conditions. Now, these are active constraints because I have an equal sign here. Zeta I plus and zeta I minus have to be greater than or equal to 0. But since they are exactly equal to 0, these constraints are active now. Hence, mu I plus and mu I minus are strictly greater than 0. But since mu I plus lambda I plus, these 2 quantities add up to C, I can infer that mu I plus is equal to C. Likewise, mu I minus is also equal to C. So for these set of points, lambdas are equal to zeros, the mu's are equal to C, and the zeta, the errors, are equal to 0. We cannot compute the bias because we have an inequality sign here, the less than sign here. So we cannot, this is not an equality from which we can obtain the bias. So the bias cannot be computed from these points which are strictly inside the allowable region, the tolerance region. And these are not support vector either because lambda I plus and lambda I minus, the Lagrange multipliers, are also equal to 0. Now let's look at a point that's exactly on the margin. Since it's a blue point that's above the hyperplane, so we have this constraint being active. So yi minus w transpose xi plus b is exactly equal to epsilon. This is our epsilon. And the other constraint, of course, is inactive. Hence, since it's exactly on the margin, there is still no error. Zeta I plus is equal to 0, and zeta I minus, because it's not down below the margin, so zeta I minus is equal to 0. Since this is an active constraint, lambda I plus is greater than 0. This is an inactive constraint, so lambda I minus is equal to 0. And since Zi plus and Zi minus are exactly equal to 0, they are active constraints, whence mu I plus and mu I minus are both greater than 0. Now, since lambda I minus is equal to 0, mu I minus has to be equal to C, because the two should add up to C. Lambda I minus plus mu I minus equals C. And since lambda I minus is 0, mu I minus is equal to C. Lambda I plus is greater than 0 and mu I plus is greater than 0. So they are both strictly between 0 and C. Neither are the lambda I plus or mu I plus equal to 0, nor are they equal to C. Now, since we have an equality here, we can compute the bias. We know epsilon. Epsilon is a parameter of the support vector machine that we decide, and yi and xi are part of the sample. They are samples, and w is the weight which we will compute. Actually, we need not compute w, as we'll see when we do the dual later on. But since these are all known, so I can compute the bias using this expression. So the bias can be computed for points where lambda I plus is strictly between 0 and C. It's neither equal to 0 nor equal to C. And these are also support vectors, because lambda I plus is greater than 0. Now, just like I have a blue point here, which is above the hyperplane and on the margin, I show this where I have a red point which is exactly on the margin and below the hyperplane, and I have these set of equations in an analogous manner, right? And so these we can also use to compute the bias. Here lambda I minus is strictly between 0 and C. And there are also support vectors, because lambda I minus is greater than 0. Now let's look at points that are outside the tolerance region. So this blue point here has an error Zi plus, and remembering that this is epsilon, we have this first constraint is a active constraint. But the other constraint, which is for points that are below the margin, we have a inactive constraint here. Hence, Zi plus is greater than 0, it's strictly greater than 0, and Zi minus is equal to 0. These are the errors. Only Zi plus is greater than 0. Since this is a active constraint, lambda I plus is greater than 0. Since the second constraint is inactive, lambda I minus is equal to 0. And we can guess what mu I plus and mu I minus will be. Mu I plus, because this is inactive, mu I plus is 0. Because the fourth constraint here is active, mu I minus is greater than 0. Now, since we know that lambda I plus and mu I plus should add up to C, and mu I plus is 0, whence lambda I plus automatically becomes equal to C. Likewise, since lambda I minus is 0, and mu I minus and lambda I minus add up to C, so mu I minus is equal to C. We cannot compute the bias. Although I have an equality sign here, this lambda I plus is a primal variable, and if I use the dual, I don't have access to the primal variables. So I cannot use this point to compute the bias. And remember, here lambda I plus is equal to C. Is this a support vector? Yes, it's still a support vector. But when lambda I plus is exactly equal to C, I still cannot compute the bias. Now, this is the analogous set of equations for the red point, which is well below the tolerance region. We cannot compute the bias since zeta I minus is not known, and these are support vectors too. So let's go back. These are the points which lie exactly on the borderline of the margin, and these will be used to compute the bias. So for the blue points, lambda I plus is, this is plus, is strictly between 0 and C, and so I collect all those points, and that's my set B plus. And likewise, this is a minus actually, this is a minus here for points like this one, which are exactly on the margin and below the hyperplane. Zeta I minus is strictly between 0 and C, and I collect those points. Lambda I minus is strictly between 0 and C. I collect those points, and that's my set B minus. So these B plus and B minus points will be used to compute the bias. Now our support vector regression is ready. So this is the dual, which we have already seen. This is the objective function that we want to maximize. This is our kernel, and these are our constraints. And remember that lambda is a vector that's twice the number of sample points. The bias will be obtained like this, and we have B plus and B minus, the two set of points. And then here, if you see, I have plugged in the expression for W, so I don't have the W here. And what I'm doing is I'm taking the summation over all points B plus and all points in B minus, and then I'm dividing it by the total of such points. That's why this is the average value of B that I'm getting. And these are the set of support vectors for which lambda k plus is greater than 0, union k where lambda k minus is greater than 0. So either lambda plus or lambda minus being greater than 0 gives us the support vectors. And this is our classifier. It's not a classifier, excuse me, it's a regressor. So y, the estimated value of y is equal to this. Summation lambda I minus minus lambda I plus times the kernel matrix plus B. The end.